welcome to today's HAO colloquium. Very happy to Dr. Savita Mathur here from Space Science Institute, Space Science Institute. Some data of Savita. Savita received her PhD in physics from the University of Paris 11, studying gravity modes and the dynamics of the solar core. And then she spent time in Europe, Asia, and North America. First visited the Max Planck Institute at Katlenburg-Lindau, working on SDO, and then spent 2 years at Indian Institute of Astrophysics at Bangalore, India as a Chandrasekhar postdoc fellow. After that, in 2010, she came here as an HAO postdoc fellow, working on Kepler observations. And she's now a research scientist at Space Science Institute. Her research focuses mainly on the Asteroseismology, and today she's going just to discuss just that. And I should mention that another vibration mode she's interested, she specializes in is violin. And this weekend you can attend the Halloween concert if you want, and spot her in the band.
Thank you, Henley, for this presentation. So I'm very happy to be here to talk about some of the work I've been doing the past few years. So I'll talk about how we can use asteroseismology to improve our knowledge of dynamics of solar-like stars using mostly Kepler data. So this is just a brief outline of this talk. So I'm going first to talk about what we already know about solar and stellar magnetic activity based on classical observations. Then I'll introduce what we can do with seismology and what it can bring, what recent results we had with seismology on dynamics, rotation, and magnetic activity of solar-like stars. And I'll finish with some summary and some perspectives. So let's start with solar magnetic activity. So since we're at HAO, you all know what solar magnetic activity is about, but I just wanted to show you how it really impacts our daily life by perturbating our GPSs or creating these amazing aurora. But even though this looks like that magnetic activity is something that is very random, there is some regularity in the pattern of the solar magnetic activity that you can see with these appearances and disappearances of the sunspots during different cycles, leading to this 11-year cycle or 22-year cycle if you take into account the magnetic polarity reversal. And even though with the sun we have lots of data, several decades of data and high resolution observation, we still have to really better understand the detailed mechanism of the solar magnetic activity. For instance, we can't really well predict the length or the strength of the future magnetic cycles. So why should we study other stars? The sun is only one star in this HR diagram. It is one point actually at a given age, given effective temperature with a given internal conditions like the given rotation rates at the surface. And so if we put the sun into a broader context, maybe we can better understand what different internal conditions in the stars impact the different behaviors in stellar magnetic activity and are responsible for the different observations that we can make. So that makes this solar-stellar connection. So there have been several surveys that have been done to study the stellar activity based on mostly calcium HK observations. So here you have a sample of the Mount Wilson survey stars. So you have the S-index as a function of the time for several stars. So this S-index gives you an idea of the photospheric activity in the stars. And you can see that you have different types of variability for these stars. So you have stars that are more or less flat, other stars that show regular cycles, some have some variability but without any regularity. So what's the reason behind these different behaviors? That's one of the questions I would like to answer. Though we are not there yet, but that would be the ultimate goal of my work. The other thing that these surveys have shown that there is these kinds of relationships between the cycle periods and the rotation periods of the stars. So this has been shown by Sarr and Brandenburg and also Bohm-Vitense. So this is also based on the Mount Wilson stars, and you can see that there are two different branches that come out from these studies, the active branch and the inactive branch. We still don't really understand what's the reason of having these two different branches. One reason might be that the dynamo process is happening at different locations inside the stars. I also put here the sun in between, so this showing that it seems to be a peculiar star, behaving very differently compared to the others. And I also added a few stars that I'm going to talk about, like HD 4933 here, for which we don't have a definite cycle, but we have an upper limit a lower limit on the cycle period. So all these observations can lead to many issues. So here is a non-exhaustive list of some issues that we can tackle. So I talked about the solar magnetic activity, for which we don't have very precise predictions so far. We also need to understand what is the relationship between the rotation period, the cycle period, and the internal properties of the stars. Why do we have some stars that show cycles, others that do not? Besides, this kind of study is also very interesting in terms of planet habitability zones, because when you have a host star that is very active, it can sweep away the atmosphere of the planet, so that the habitability is no longer valid for these planets. Then many people have also started to work on gyrochronology, trying to find relationships between rotation and ages, so you can hopefully use measurements of rotation, which is easier than measurement of ages, to have determination of ages without using any models. So that's something that I'm interested in as well. So we've seen that most of the observations of magnetic activity are based on what's happening at the surface of the stars. But it's actually also related to what's happening inside the star. And so we need to understand, to know what's going on inside the stars. And that leads me to seismology, because that's the only method that allows us to probe these deep layers. Okay, so here I'm just going to remind you a few things about seismology. So because the star is like a resonant cavity, you have different oscillation modes that propagate, and they are characterized by their degree, the azimuthal order, the radial order. And so in stars like the sun, you have two types of modes that propagate, the acoustic modes, for which the restoring force is the pressure. And they have this property of being equidistant in frequency. So I will come back about that later. And so these modes are actually excited by the turbulence in the outer layers of the convection zone. So you can see some representation of these modes here, which are reflected at the surface of the star. Then you also have gravity modes, for which the restoring force is buoyancy. Fortunately, because of the unstratified way in the convective zone, they are evanescent in the convective zone. So that makes them very difficult to observe. But they're very interesting because they spend most of their life in the radiative zone and carry a lot of information about what's happening inside in the deeper layers of the stars. And these modes have the property of being equidistant in period compared to frequency and for the acoustic modes. And here I just wanted to show you a propagation diagram of these modes. So you have the gravity modes here and the acoustic modes at the surface of the stars. Then you also have what we call the mixed modes. So these modes have a P mode character in the envelope of the stars and a G mode character in the core of the stars. And they result from the fact that there is a large density gradient between the core and the envelope of the stars, and it makes the star is divided into two coupled cavities. And so you have this coupling between the acoustic and the gravity modes, and they're very interesting because being sensitive to both the core and the envelope, we can detect them, and they give us information, very precious information about the core of the stars. So as I said, seismology is the only method that directly probes the deeper layers of the sun and the stars. So here I'm just showing a classical power spectrum for the sun. So you have the density power as a function of frequency. And you can see this background, which is due to the convection, on top of which you have these peaks that correspond to the acoustic modes. Then you have this region where we expect to have gravity modes. So I didn't say this is based on Gulf observation, so on Doppler velocity observation. Like we can have similar things by doing photometric observations. And one interesting thing that you can see is that in the background, you can have information about the granulation and the supergranulation in the sun. But one interesting quantity that we can easily get from this power spectrum is the frequency of maximum power, the nu max here, which is actually proportional to the gravity of the star. So this is one quantity that is very interesting for us. Then if you zoom into the acoustic modes, you can see that you have this very regular pattern that is repeated in the power spectrum. So you have aliquot 3, 1, 2, 0 modes that are repeated with a frequency of delta nu, which is the mean large frequency separation. So here I just put a piano to show that it is similar to having the octave that is repeated on the piano. And so this mean large frequency separation is actually proportional to the mean density of the star. So we saw that we have already two quantities that we can have easily, and that already give very crucial information about the gravity and the density of the stars. Here I just wanted to show you another way of representing the power spectrum, which is the HL diagram that was introduced by Gerard Grech 30 years ago. So basically, how is it done? It's you take chunks in the power spectrum here of length delta nu, and you stack them one on top of each other, just like stacking all the octaves of the piano. So here in the piano you have all the do, re on top of each other. So here you have all the L equal 2, 0, and 1 on top of each other. And this is an easier way to sometimes identify the degree of the modes that we are observing.
Separation in the modes?
Yes, in the P modes.
So is the average density the density of the convection zone where they propagate, or the entire star?
Of the entire star? Oh, well, yeah, I would say the entire star, yeah. Because also, so some of the acoustic modes, if we come back here, some of the acoustic modes, the low degree acoustic modes also go a bit deeper compared to higher degree acoustic modes. So they are also probing the interior, the core. Okay. So we have the maximum power frequency and the mean large separation. So we can use these scaling relations that have been developed a few years ago. And so by combining the knowledge of nu max and delta nu, you can, and the effective temperature of the star, we can have a first estimation of the radius and the mass of the stars without using any model, and with precisions that are usually much better than what we can get only spectroscopically. So this is very interesting for people looking for exoplanets, because if we can get the radius of the star with a very good precision, then the radius of the planets that are transiting these stars can be obtained very easily. So these relationships have been tested both theoretically and observationally by comparing values that we obtain with seismology, but also with classical observation like interferometry or parallax, hyperacous parallaxes. And we found that there was a very good agreement between these different methods. So validating the scaling relation. Another way to show these scaling relations is to plot the delta nu as a function of nu max for a large sample of stars. And you can see that this relationship is valid from solar-like stars on the main sequence down to the red giants. The color code here represents the amplitudes of the modes, and you can see that the amplitudes of the modes increase while you have more and more evolved stars, because they become more and more luminous. So it impacts the amplitudes of the modes.
You have two scaling relations, one period of density. So are there stars for which you only get the period of the frequency of the power?
Yes, of course, for stars with low signal-to-noise ratio, sometimes we just see a bump, and when, we don't see the modes individually. But even though we don't see the modes individually, just by looking at the periodicity in the frequency, we can still measure a kind of delta nu. We don't have the frequency of the individual modes, but we see some pattern that is repeated. Well, one is proportional to the density, and the other one to the gravity. So that's how it's different.
Oh, okay. You don't. I thought you knew all those, like how all this
Yes, I think so. Well, well, these relations agree also with what we get from the models. So it's, yeah. Okay, so that's from the classical scaling relations. But lately, a few years ago, we have also studied the background and the power spectrum. And so I was saying that we can have information about the granulation in the power spectrum here. So usually what we do here is to fit a function which has a component of white noise, Harvey-like, what we call the Harvey-like function, and this Harvey-like function has depends on an exponent alpha, which gives you the slope of this function here, and tau gran, which is the time scale of the granulation, is given by the position of this knee. And by analyzing a few hundred red giants, we've shown that this granulation timescale is tightly related to the position of the frequency, maximum power in the frequency. And we know that nu max is related to granulation, so just by getting the timescale of the granulation, we can have the gravity of the star. And that's something, well, I mean, this relationship is something that you would expect because, well, granulation is related to convection. Modes are excited by the convection, so there should be some relationship between the two. And then we've showed that this relationship between the time scale of the granulation and the log G is valid for red giants here in red and solar-like stars here. So even if we don't manage to measure individual acoustic modes or even to detect acoustic modes just by using the property of the granulation in the power spectrum, you can already have a pretty good estimation of the gravity of the stars. So that's something that is new, and we can use that even for low signal-to-noise ratio stars. Okay, so that's all for all the scaling relationships and what we can get on the properties, fundamental properties of the stars. I'm going to move to what we can get on, what information we can get on the rotation and the magnetic activity of stars, solar-like stars. So we know that for a star like the Sun, the magnetic activity can be explained with dynamo theory. And here I just wanted to point out what kind of information we need, or what we already have concerning stellar magnetic activity. So this dynamo process is actually the result of the interaction between convection, rotation, magnetic field. So in the dynamo models, one of the interesting quantities is the depth of the convective zone. Then we also need to have measurements of magnetic field, cycle period, rotation period, if we can also the internal rotation profile of the stars. And in red, I just put the parameters that we can have with spectroscopic or spectropolarimetric observations, so magnetic field, cycle period, and V sin I. So we're still lacking these other quantities like depth of the convective zone or rotation profile. So that's where seismology comes into play. So here I just wanted to show you, well, this is still now an old diagram because we have much more stars now, but how the picture for seismology has changed in terms of number of stars that we had, where we had a few tens of stars before 2007, and now we have several 20,000 solar-like stars and red giants. So we are just a little bit drowning with all these data sets, but we still try to figure out very interesting things from them. So one of the things we can do for stars where we have a high signal-to-noise ratio is to do some stellar modeling in order to get information on the internal structure of the stars. So basically you have stellar models that include a bunch of physical processes. This is a very non-exhaustive list. And what we try to do is to find the best match between the observables and the model. And so the classical observables are the spectroscopic ones, but now we also have all the seismic ones, delta nu, nu max, and individual frequencies of the acoustic modes. So different techniques can be used to model the stars. You can use a grid of models or do what Travis developed here with the Asteroseismic modeling portal with a genetic algorithm where we compute thousands and thousands of stars to find the best fit to our observables. And especially with this technique, we showed that we can have a much better precision in terms of the determination of mass, radius, or ages of the stars. So this is an example of for the HATP7b, so that was the constraining with spectroscopic for the radius of the star, and just by using all these models, you can really pinpoint the radius of the star. The other thing that we can get, because we are using so much more information with all these acoustic modes frequencies, is the structure of the star, in particular the base of the convection zone. So of course I'm not saying that we have a definite measurement of the base of the convective zone of all the stars, but we have an idea because this is based on models that have given physics. We know that they are not complete, but this is still a beginning. So this is one of the quantity that we can get, and that is important for dynamo models. So now I'll move on to surface rotation. So because, well, not all of the stars are active, but when a star is active and has spots on it, you can see how this light curve is modulated by the passage of these spots on the visible disk of the stars. And this modulation is proportional to to the rotation rate of the star. Of course, if the star is not active, then you only have a very flat light curve and you can't measure the rotation period. So we need an active star to be able to measure the surface rotation just by using photometric data. So from there, you can use different methods like computing periodograms, time frequency analysis, or computing autocorrelation functions. Maybe I just say that with the periodogram, one of the main issue with that technique is that sometimes you can get the first harmonic or the second harmonic, and you have some factor of 2 or 4 between the real period of the star and what we are measuring. Which with the time frequency analysis and the autocorrelation, we can get rid of most of the time. So we've analyzed a sample of 500 solar-like stars for which we had detected acoustic modes. So here you have a kind of modified HR diagram where you have all the sample of star where we could measure surface rotation. So to measure this surface rotation, we used the different techniques I talked about earlier, and we only picked out the stars for which all the techniques agreed with the rotation period that came out, so that we have a very robust estimation of the rotation period at the surface. Here we just divided the stars into 3 different categories. So in blue you have the cool stars, in red the hot stars or F stars, and in green you have more evolved stars, the subgiants stars. So we did a little bit of distribution analysis of these stars, and one interesting thing that you can see here, so you have the histogram as a function of the rotation period of the stars, and you can see that the red, so the hot stars, seem to be rotating much faster than the other stars. And that's something that we do expect from theory. Like if you know about the Kraft break, you have these more massive stars, more massive than 1.2 solar mass. They have very thin convection zones, so they are less affected by magnetic braking, so they are not slowed down as much as the cooler stars. So you expect them to be rotating much faster than other stars. So here I was just also showing, so I'll come back to that maybe later, how the activity of these stars can be. So we compute a magnetic index based on photometric data, and so I'll describe it later, but you also see that the hotter stars seems to be more active than the cool and the subgiant stars. So from there, because for these stars we had observation of the individual modes, acoustic modes, there were some stars for which we had models giving age estimations for these stars. So here you have a bunch of stars that were modeled with AMP, so you have the rotation period that we have measured as a function of the age. And you can see that there is a clear relationship between these two quantities, and this relationship actually agrees with what has been published in the past for cluster stars, younger cluster stars. So this is for field stars and much older stars, and the relationship is still holding up. So that's good, at least for this sample of stars. So that was for the surface rotation periods. But if we go to seismology, we also know that rotation affects the acoustic modes. Because of the rotation, there is a lift in degeneracy in the modes. And instead of observing single peaks for the L equal 1 and 2 modes, you will have splitted modes. And the splitting will be, so the difference between the two components of a single mode will be proportional to the rotation rate of the star. And depending on the mode, depending on which regions of the star the mode is probing, you will have different information about the rotation at different layers of the stars. The other, maybe one of the issue with that is still comparable to the spectroscopic observation, is that this is still dependent on the inclination angle of the star. So we have rotation splittings, but the inclination angles of the star is also has to be taken into account, because the inclination angle of star will change the ratio between the different components observed for each modes. So yeah, so now if you observe a star pull on, then you will again see only one single peak, because there won't be lift-up degeneracy. So for the sun, we had lots of modes for which we measured splittings, and we could do some inversions to have this very nice rotation profile. Unfortunately, because we don't have gravity modes, we can't go beyond 0.2, 0.3 solar radius. So we know the rotation profile of the sun down to the almost the core, but we lack this kind of information that gravity modes are very crucial to do that. On the other hand, that's what we can do with Kepler targets. So, of course, with Kepler data, we only have very low degree modes that are detected because it's not resolved. So we have L equals 0 to 3 modes, up to 3 when we are lucky. So this is the case of a subgiant. So this is a subgiant, so we have mixed modes because of the coupling between the envelope and the core cavities. And so you can see here that instead of having just a line for the L equal 1 mode, you see some departure from the straight line. And if you zoom in, I'm not sure if you can see it, but if you zoom in, you could see that instead of having one single mode, we actually have different components. So for this star, for this subgiant that we call Otto, we could measure splittings for the mixed modes. So because these mixed modes, so you have, so the mixed modes can be either more sensitive to the core or more sensitive to the envelope. They can provide information about the radial differential rotation in the star. So you have information about the surface rotation, but also of the core rotation. So for this star, we can see that the core is rotating faster than the surface of the star. And this is really amazing because we've seen that for the sun, we can't get the rotation of the core, but for subgiants, we can get that. Though we don't have the whole profile, of course. So you can do some inversions, but we have mostly points here, and anything can happen between. But at least we know that it's rotating faster in the core than at the surface. So here I'm just coming back on the stars for which we measured the surface rotation using only the photometric data. And we compared that, so let me remember. So you have the rotation, the surface rotation as the x-axis, and this is the rotation that comes out from splittings measurement for these solar-like stars. And you can see that there is a pretty good agreement between these two independent measurements of the surface rotation of the stars. Of course, we still have a few stars where there is a factor of 2 difference, but they are very minimal. So this is still a work in progress, but this is very encouraging that we are measuring the surface rotation of these stars. Okay, so that was the part on the rotation. So now let's move on to the magnetic activity of the stars. So this is again the sun, since it's our basis here. So here we've done some time frequency analysis of some Virgo data. So you can see that, so you have the period as a function of time, how the rotation period changes with time. We see that most of the power is around 26 days, but it's very patchy here. And because you also have the first harmonic, so 13 days rotation that comes out in the data. The other thing that you can do is if you project this wavelet power spectrum on the time axis, you get this kind of proxy, which is very similar to the magnetic proxy that we can get with the radio F10.7 observations or calcium HQ observations. So this is also a way to get a proxy of the magnetic activity with time. The other thing that we know for the Sun is that when magnetic activity changes, the amplitude and the frequencies of the modes also change. So here in red, you have the sunspots as a function of time. And here you can see how the amplitudes of the modes are anticorrelated with the activity of the Sun, while the frequencies shift towards higher frequency when the magnetic activity increases. So this is something that has been observed only for the Sun, and this is something that we could use for other stars, right? So that's what we did with the core target HD 49933. It's a F dwarf, more massive than the Sun. So it was observed in three different runs, actually. Here I'm just showing two of them, and it's rotating with a rotation period of 3.4 days, so very fast. Yeah.
I have a question. I don't know. Why do the frequencies change for an active star? Is that because the
it's
itself, the waves are bouncing up a different height? Magnetic field is.
I think it's going to change the local temperature, I guess. So then the sound speed is going to change as well. So it's going to. I'm not sure we know exactly. Yeah. I don't think we know exactly what it's doing. There are several things.
That theory suggested it's a direct magnetic perturbation, but also associated changes in the temperature and the turbulent velocity of the surface. So it basically just changes the outer boundary.
So for this star, we had this very nice power spectrum, so we could detect individual acoustic modes. And so we did the similar analysis as we did for the Sun. So here you have the changes of the amplitudes of the modes, the frequency shifts. And you can see that during the second run, we had this very nice anti-correlation between these two quantities, similar to what we had for the Sun, suggesting that there is some activity going on in this star. Fortunately, we didn't have enough data to get an idea on the cycle period. It's at least of 120 days, which is the longest data set that we had for this star. But after that, we also started to follow up this star with calcium HK with this Mars project, and it confirmed that it has a quite high S-index compared to the Sun, so it's indeed an active star. And you can see that there is some variability. Unfortunately, we had some gaps, and then the telescope stopped, so we don't have more data sets for this star, unfortunately. But that was the first time we could observe these changes in the seismic parameters of the star due to magnetic activity in a star different than the Sun. It's from Coral. Yeah. Okay. Okay, so that was how magnetic activity can affect the acoustic modes. But we can also use just the photometric data to have some idea about the magnetic activity, because we know that if we measure rotation periods of the surface, we have activity going on at the surface of the star. So you can compute standard deviation of the time series, or because we know that rotation and magnetic activity are related, we can use this information to compute some kind of standard deviation of subseries of length proportional to the rotation period of the star, so that we are sure that it's something related to the magnetic activity of the star. So that's what we call the average SPH index. And we can also compute a kind of contrast term. So if you compute this standard deviation on subseries of length 5 times the rotation periods, you get, again, this kind of magnetic proxy for this star. And you can only take a subset of points that are below the mean value of SPH, or the subset of data where you have standard deviation higher than the mean SPH, and compare these two values, and that gives a contrast between the highest level of activity that you can have in the star and the lowest level of activity you can have during this observation time. So here I just come back to some of the surface rotation stars, and I'm going to focus on these. Yeah, I'm going to talk about it again, but
Basically, just when you see various activity indices for the sun, like that.
right.
But, it's the same story on other stars. You see low frequencies go up, you get more calcium. You get more.
You mean compared to frequencies of the mode? Is that what, compared to seismology?
You get a different story.
Well, there is only one star where we saw these frequency shifts, except the sun so far, so we haven't. And the data from the calcium HQ were not contemporaneous, so we couldn't compare them. So.
It'll be interesting.
Yes, yeah, that would be definitely something to. Yeah. Yeah, maybe there are some stars where when the activity index increases, the frequency go lower or higher. I mean, the opposite way to the sun. So. Okay, so here I'm going to focus on stars that rotate quite fast, because we've seen that there is this relationship between rotation period and cycle periods. So the faster the star is rotating, the shorter cycle period we would expect for the star. So yeah, you might wonder why there is the Jungle Book here. So you understand now. So this is one of the stars. So instead of calling them with their kick number, which become too long, we just give them names. So this is Ka. And so this star has a rotation period of 2.2 days that you can see around here. And if you look at this, the magnetic proxy, you could see that, oh, it looks like there are at least 2 cycles that have been observed for this star. So we were like, yeah, another star with cycles. Unfortunately, when we looked into more details at the spectrum of the star, we saw that there were close to the rotation period frequency that we found, there were actually 2 peaks very close to each other. And the beating of this peak was exactly giving this periodicity that we observe in the data. So this is just a result of the beating of these two close frequencies. But on the other hand, one interesting thing is that this beating is coming because we have spots coming all the time during the observation. So it seems that there is either active longitude on this star, making all the spots coming at the same longitude during the whole observation time. It could be also that there is a close companion that generates the spots that we are observing, and the spot is always there.
I have a question.
Yeah.
If you were looking at that star at the pole, and it had sunspots at some point on it anywhere, wouldn't you just then always see sunspots? I realize you have to be looking at the pole. And so I'd have sunspots coming and going. As long as I had a sunspot, I would have continuous.
Yeah, that's true. Yes, that could be something. But then, so we had V Sinai observation for this star. So we have rotation periods from only the photometric data. We have the V Sinai and the radius from seismology, and by comparing them, we can get an estimation of the inclination angle, and it's not 0. So we're not observing it. No. I don't remember how much it is, but it's, I would say it's close to equatorial, like the sun. Yeah. Okay, so that's the story about Ka, but then there is this other star, Sher Khan. which is also rotating quite fast with a rotation period of 2.5 days. With seismology, we also have the mass and the depth of the convective zone, so it's a very shallow convective zone. And here again, with the magnetic proxy, you can see that we have a low magnetic activity, an increase, and a decrease. So do we have a cycle this time? Well, it looks like a cycle, and unfortunately we don't have more, so we can't say if it's regular or not. But the other interesting thing is that if you zoom into this, the high activity region here, you can see that you also have these blobs of approximately 90, 100 days. And here again, when we looked at the periodogram, we saw that there were again these two frequencies very close to each other, creating this beating of 90 days. So here again, maybe we have also active longitudes which are only present during the maximum activity of the star. So that's all kinds of information we can have. The other thing that we can study is that when you look at the wavelet power spectrum, you can see that there is a slight change in the rotation period here. So it seems to be decreasing a little bit when the magnetic activity is increasing. So is it due to spot migration? That could be one of the explanations of this change of rotation period at the surface of the star. So here I just want to show you what other things we could do with seismology. We can have also measurements of convective velocity, for instance, and have information on the Rossby numbers of the star. So here I just remind what Sarr and Brandenburg showed for a sample of Mount Wilson stars, where they didn't see any correlation between the amplitude of the cycles and the Rossby number. While in our sample of stars, so instead of the amplitude of cycle, I plot the contrast, which is kind of similar to this amplitude, but of course this contrast is also biased by the fact that we are not sure to observe a whole cycle, so it's just based on the observation length that we have. And this Rossby number, and there seems to be a small anti-correlation here, but of course this is a small sample of stars. We could be biased by the sample, but this is something that we can work further on with a larger number of stars. So here, I just wanted to come back on the SPH, and actually there was Christopher Carafe had led some observations at the Nordic Optical Telescope with calorimetric observations of 20 and something solar-like stars observed by Kepler. So I compared the SPH that we have obtained with the Kepler data with the S-index that was obtained with the calorimetric observation. And you can see that there's not much correlation like this. But if you so this point is actually the sun. So if you take into account how the sun varies from the minimum to the maximum activity, you can see that it's a big box here. So depending on at what period of the cycle we are observing these stars, maybe we are not getting the same kind of information here. So, and the other thing I wanted to point out is that for the sun, if you compare the calorimetric observation and the SPH, so here you have the SPH as mentioned of calorimetric, and you can see that while the activity is increasing, there is a nice slope here, but it seems that there is some saturation when the calorimetric increases. This is still a work in progress, but we don't understand why that would happen. So maybe we are also underestimating our SPH index when we are measuring the magnetic activity on photometric data. Okay, so that leads me to the summary. So we've seen that to this picture of the dynamo models with asteroseismology, we can have an estimation of the depth of the convective zone, changes in the frequencies and amplitudes of the modes, measurements of the rotation period, cycle period. We can also have information on the rotation profile. I didn't talk about latitudinal differential rotation. I know that Mark worked about that a little bit here. Unfortunately, the error bars that we have on the frequencies are still too big to be able to get any information about latitudinal differential rotation right now. But this is something that we could investigate into. And to finish, so this is maybe one of the next steps that we could take now. So this is another star, Dushera, which is not rotating as fast as the two previous ones with a rotation period of 9.5 days. We don't really have a cycle. It looks like that there is a decrease here and then maybe an increase of the magnetic proxy. And we tried to model that with the ASH model using a 1D seismic model as inputs for the structure of the star. And for this star, from the preliminary results, it seems that we can have cycle that establishes. I think the cycle period that Kyle obtained was about 4 years. So that's the length of data that we had with Kepler, so we can't compare them. So yeah, that's where we're at. And so for the future, you can say, okay, so now Kepler is done, but we still have more data that are going to come in the next 10, 15 years with the K2 mission that is going to observe at the ecliptic plane. We also have the TESS mission that is going to be launched in 2017, which is going to observe for Earth-sized planets in the habitable zones, focusing on bright stars. And then there is, in 2024, there is the Plato mission that is going to be a survey of half of the sky, focusing on bright stars, and particularly with this mission, because we will be able to have continuous data sets for a few months to a few years. We could actually study magnetic activity for these stars, because these two missions are only for 27 to 75 days, so that's not enough to get cycles, but it's, yeah. So I thank you for your attention.
Your slide, slightly on the saturation point. I wasn't quite sure what that was showing. This is just for the sun. What are the points?
Yes.
On the bottom part?
So I didn't do the work. David was the one who did that, but I think it's mean value of different subseries. So it's the different points here as a function of. So they were taken at the same time, I think. Yeah. So it's just how the calcium HK varies as a function of the SPH at the same time.
It reminds me of there's a saturation between X-ray and luminosity.
Yeah, but it's not the same. Yeah, that's only one star. What do you mean by characteristics of the star? Is there something? You mean in terms of magnetic activity of the star? Yeah. Well, I know that most of the planets that are found now are around M dwarfs, if I remember well. I mean, small-sized planets. Yeah, maybe I'm not the best one to talk about that, but in terms of activity, I don't remember. I know people are working on star-planet interaction and how the presence of planet can impact the magnetic activity of the stars, but I don't think it's conclusive so far. Yeah, I guess so, but yeah, I don't know anything about this work. Sorry.
So, for the Earth, we look at the sun, the cycle, over a cycle, the variation of TSI is like on the order of 0.1%. So from the analysis, the other stars you looked at, how big this variation can be between cycles from the peak and minimum cycles.
Yeah, so what's the unit of the TSI? Is it no?
The TSI is like watts or
Yeah, so okay, so here in ppm, I mean it's flux. Yeah.
Okay, so it's similar. Yeah.
Yeah.
Depth of the convection zone measurements in mathematical model. Are those typically measured by fitting for a model? I think that's what I understood from your talk. Can that be obtained without a model-free way?
Kind of. So yeah, I didn't talk about other works. So you can, so that's what we call the acoustic glitches. So because when you have a sharp feature happening in the structure of the stars, it also impacts the way the mean large separation varies from one order to the other. So you can see this kind of oscillation in the frequencies as well. And this is related to the depth of the convective zone or the second ionization of helium. And this has been done with 20 Kepler stars. And what we've shown is that there is a good agreement between the depth of the convective zone using this method and the models from AMP. So, yeah. So yeah, we can use other techniques, but we need very high signal-to-noise ratios to do this kind of analysis for the acoustic glitches. So it hasn't been done for many stars.
Maybe a follow-up question to this. Now, this is acoustic glitches. I mean, the case of the sun, the surprising result is that actually the transition from the convection zone to the radial phase theory is extremely smooth. I mean, it's much smoother than any standard convection theory. If it's overshoot or not overshoot would predict. Can you get from other stars data on the smoothness of this transition, and does the smoothness of this transition vary with stellar time?
That's a good question. I'm not sure we can do that. I don't know. Maybe Travis can say something.
I think the amplitude of the glitch signal tells you something about how smooth that transition is.
Oh, okay.
So those amplitudes have been measured from a small sample of stars, but I don't know if anybody's actually looked at.
I'm not sure. Yeah, I know that. So they were using different methods to measure these glitches, and this is kind of so they try to fit a kind of model. So that's also it's not a physical model dependent, but it's the way they fit this glitch. And there were some disagreement with the amplitudes, right? So at least they were getting the frequency right, but not the amplitude. So they don't talk about that. Yeah.
Okay, if no more questions, you can see Savita again this Saturday at Mackey Auditorium.
No, it's at the First Presbyterian Church. It's on 15th and Canyon.
At 2 and
2 p.m. and 7 p.m. Yeah.
Okay, thank you. Yeah.
Thanks.
Thanks. Boulder Symphony.
Yes. Yeah.
So do they analyze because they found a whole bunch of Earth-like planets? Do they specifically